Hi children, this is the third video of the chapter Elasticity, class 11. In the last two videos, we discussed some of the important applications on Young's modulus, bulk modulus. We will see some more on moduli of elasticity and the energy stored, potential energy stored, elastic potential energy. So we'll move on with the 24th problem. We'll see almost repeat type. One more, an example. Practice in fact. A weight of 10 kg suspended from a copper wire 3 meter length is given and diameter 0.4 mm. Its length increases by 2.4 centimeter. Now, what he has given? He has given weight. We will see whether it is useful. Length L and diameter given. So, area has to be written as pi d square by 4 and increase in length delta L. Continue. If the diameter of the wire is doubled, then the extension of the wire will be. Here he says only diameter changes. So, what do you write for the extension of the wire? You must be in a position to identify the relation by now because you have solved a lot of applications related to Young's modulus. The formula is Y, that is F divided by A delta L by L. So delta L comes to left side, Y to denominator and L to numerator. Finally, you can write delta L, that is F divided by A, L by Y. Now, diameter is given, that's why F L divided by pi d square by 4 into Y. Since Y is a constant, same wire, same length, no change in length, no change in weight. Only thing that changes in the problem is diameter. So inverse relation. Diameter is in the denominator. Relation between extension and diameter, inverse. Square of diameter. He wants diameter in the extension in the second case. So write delta L. You must be in a position to write this way directly. ನೋಡಿ ಡೆಲ್ಟಾ L2 ಸೆಕೆಂಡ್ ಕೇಸ್ನಲ್ಲಿ ಎಕ್ಸ್ಟೆನ್ಷನ್, ಡೆಲ್ಟಾ L1 ಫಸ್ಟ್ ಕೇಸ್ ಎಕ್ಸ್ಟೆನ್ಷನ್. ಇಫ್ ಯು ಡಿವೈಡ್ ದಿಸ್ ವೇ, you must be in a position to write d2 directly in the denominator and d1 corresponding to diameter in the first case numerator because inverse relation delta L1 denominator d1 numerator. Delta L2 numerator d2 denominator raised to the power 2. How do you write this? Because delta L1 proportional to 1 by d1 square. Delta L2 proportional to 1 by d2 square. That's very simple analysis. We have solved several problems of this type by now in physics. That's why I can easily analyze, solve for delta L2, d2, and he has given the values of d1. d1 is given. We'll come to that. What is d2? He says diameter is double, that is 2 times d1. Here d1 cancels. You need not the value of diameter also. Diameter not required here. Just the ratio is given, relation. d1, d2 2 times d1. That's it. d1 cancels. And delta L1. You are transferring delta L1 to the right side. So, in the bracket you are left with 1 by 2 squared and delta L1. First case extension 2.4 in centimeters. That's why delta L2, that is 1 by 4 times 2.4. That is 6 4s are 24, 0.6 meters. Very simple. Within 30 seconds you can try this problem. Now on stress strain curve graph. Strain stress curve of 3 wires of different materials are shown in the figure. PQR are elastic limits of the wires. The figure shows that. Actually, students, you learned in regular class stress strain curve. Taking stress along x-axis, strain along x-axis, stress along y-axis, plotted a graph. And you found slope. What is slope? Slope that equal to tan theta. And that slope represents stress divided by strain. Stress by strain. Why? If you construct a triangle to this line, stress strain curve, this is change in strain. This is corresponding change in stress. Tan theta is opposite by adjacent. Opposite side nalli you have stress and adjacent side nalli you have strain. And stress by strain is modulus of elasticity. For a wire it is Young's modulus. So Young's modulus is tan theta, stress by strain. The material which has more stress is more elastic. That is the idea. ನಾರ್ಮಲ್ ಯೂಸೇಜ್ನಲ್ಲಿ ರಬ್ಬರ್ ಈಸ್ ಮೋರ್ ಎಲಾಸ್ಟಿಕ್. ವೈ? ಇಟ್ ಈಸ್ ಮೋರ್ ಫ್ಲೆಕ್ಸಿಬಲ್ ದ್ಯಾನ್ ಸ್ಟೀಲ್. ಬಟ್ ಅಕಾರ್ಡಿಂಗ್ ಟು ಫಿಸಿಕ್ಸ್, ದಿ ಸಬ್ಸ್ಟೆನ್ಸ್ ವಿಚ್ ರಿಕ್ವೈರ್ಸ್ ಮೋರ್ ಸ್ಟ್ರೆಸ್ ಈಸ್ ಮೋರ್ ಎಲಾಸ್ಟಿಕ್. ಅದು ಪಾಯಿಂಟ್ ಯು ಹ್ಯಾವ್ ಟು ರಿಮೆಂಬರ್. ಅಲ್ಲಿಗೆ ಸ್ಟೀಲ್ ಈಸ್ ಮೋರ್ ಎಲಾಸ್ಟಿಕ್. ವೈ? ದಟ್ ರಿಕ್ವೈರ್ಸ್ ಮೋರ್ ಸ್ಟ್ರೆಸ್ ಟು ಚೇಂಜ್ ದಿ ಡೈಮೆನ್ಷನ್, ಟು ಚೇಂಜ್ ದಿ ಶೇಪ್ ಸೈಜ್. ದಟ್ಸ್ ವೈ ಸ್ಟೀಲ್ ಈಸ್ ಮೋರ್ ಎಲಾಸ್ಟಿಕ್. ಸ್ವಲ್ಪ ಸ್ಟ್ರೇಂಜ್ ಅನ್ಸಿದ್ರು ಈ ಥರ ಯೋಚನೆ ಮಾಡಬೇಕು. ನಾವು ವಿತ್ ದಟ್ ಐಡಿಯಾ ವಿಲ್ ಅನಲೈಸ್ ದಿ ಗ್ರಾಫ್. ದಿಸ್ ಗ್ರಾಫ್ ಈಸ್ ಆಪೋಸಿಟ್. Why? Because along y-axis you have taken strain and x-axis you have taken stress. It is strain-stress graph. Now you find slope. What is slope in this? Slope is tan theta. ನೀವು ಈ ಥರ ಇದಕ್ಕೆ ಟ್ರಯಾಂಗಲ್ ಕನ್ಸ್ಟ್ರಕ್ಟ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಫಾರ್ ದಿಸ್ ಆ್ಯಂಡ್ ಆಲ್ಸೋ ಫಾರ್ ದಿಸ್ ಯು ಕನ್ಸ್ಟ್ರಕ್ಟ್ ಟ್ರಯಾಂಗಲ್ಸ್. This is angle theta, this is angle theta, this is angle theta. For each graph, what is tan theta? Tan theta is opposite by adjacent. Opposite here is change in strain. Change in strain. Divided by adjacent side is change in corresponding change in stress. Therefore, ನಾವು ಯಂಗ್ಸ್ ಮಾಡ್ಯುಲಸ್ ಬೇಕು ಅಂದ್ರೆ ಏನು ಮಾಡಬೇಕಿಲ್ಲಿ? 1/ಸ್ಲೋಪ್ ಮಾಡ್ಕೋಬೇಕು. ವೈ? ಬಿಕಾಸ್ ಇಟ್ ಈಸ್ ಸ್ಟ್ರೇನ್ ವರ್ಸಸ್ ಸ್ಟ್ರೆಸ್ ಕರ್ವ್. 1/ಸ್ಲೋಪ್ ಮಾಡಿದಾಗ 1/tan theta, that represents some change in stress divided by corresponding change in strain. That's very important. ಹಾಗಾದರೆ in this graph, strain versus stress, 1/slope is Young's modulus. This itself could be a problem. ಇಷ್ಟೇ ಒಂದು ಪ್ರಾಬ್ಲಮ್ ಮಾಡ್ಬೋದು ಅವರು. Now let's come to this, the 3 wires. ನೋಡಿ ಇಲ್ಲಿ ಆರ್ಗೆ ಇದು ಎಲಾಸ್ಟಿಕ್ ಲಿಮಿಟ್. ಲೆಟ್ಸ್ ರೈಟ್ ದಿಸ್ some capital S. ನೋಡಿ ಇದು ಸ್ಟ್ರೆಸ್ಸು. ದಿಸ್ ಈಸ್ ದಿ ಕರಸ್ಪಾಂಡಿಂಗ್ ಸ್ಟ್ರೇನ್ ಫಾರ್ ಆರ್. ಲೆಟ್ ಅಸ್ ಮಾರ್ಕ್ ದಿಸ್ SR, ದಟ್ ಈಸ್ ಸ್ಟ್ರೆಸ್ ಕರಸ್ಪಾಂಡಿಂಗ್ ಟು ದಿ ಎಲಾಸ್ಟಿಕ್ ಲಿಮಿಟ್ ಆಫ್ ದಿ ಥರ್ಡ್ ಕೇಸ್ ಆರ್ ಪಾಯಿಂಟ್. ಇದು ದಿಸ್ ಇಸ್ ಸ್ಮಾಲ್ ಎಸ್ ಆರ್ ಬರೆಯೋಣ. ವೈ ಸ್ಮಾಲ್ ಎಸ್? ಅದು ಸ್ಟ್ರೇನಿಗೆ ಬರ್ದಿರೋಣ. ನಾವು ಕರಸ್ಪಾಂಡಿಂಗ್ ಟು ದಿ ಕರ್ವ್ ಕ್ಯೂ ಇಸ್ ದಿ ಎಲಾಸ್ಟಿಕ್ ಲಿಮಿಟ್. ಅಲ್ಲಿಂದ ಲೈನ್ ಡ್ರಾ ಮಾಡ್ಕೊಳ್ಳಿ. ದಟ್ ಮೀಟ್ಸ್ ವಿತ್ ದಿ ಸ್ಟ್ರೆಸ್ ಕರಸ್ಪಾಂಡಿಂಗ್ ಟು ಆರ್. ಸೊ ಸ್ಟ್ರೆಸ್ ಕರಸ್ಪಾಂಡಿಂಗ್ ಟು ಈ ಕೇಸ್ನಲ್ಲಿ ಸ್ಟ್ರೆಸ್ ಕರಸ್ಪಾಂಡಿಂಗ್ ಟು ಕ್ಯೂ, ದಟ್ಸ್ ಈಕ್ವಲ್ ಟು ಸ್ಟ್ರೆಸ್ ಕರಸ್ಪಾಂಡಿಂಗ್ ಟು ಆರ್. ಬಟ್ ಲುಕ್ ಅಟ್ ದಿ ಸ್ಟ್ರೇನ್ ಲೆವೆಲ್ ನೋಡಿ ಇಲ್ಲಿದೆ. ಟು ದಿ ಕರ್ವ್, ಥರ್ಡ್ ಕರ್ವ್, ಮಿಡ್ಲ್ ಕರ್ವ್, ಎಲಾಸ್ಟಿಕ್ ಲಿಮಿಟ್ ಕ್ಯೂ ಇರೋ ಕರ್ವ್. ಅದರದ್ದು ಸ್ಮಾಲ್ ಎಸ್ ಬರೆಯೋಣ ಫಾರ್ ಸ್ಟ್ರೇನ್ ಕರಸ್ಪಾಂಡಿಂಗ್ ಟು ಕ್ಯೂ. ಇಲ್ಲಿ ಏನು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ತೀರಾ? ಬಟ್ ಎಸ್ ಕ್ಯೂ ಈಕ್ವಲ್ ಟು ಎಸ್ ಆರ್ ಅಂದರೆ ಕ್ಯಾಪಿಟಲ್ ಎಸ್ ಕ್ಯಾಪಿಟಲ್ ಆರ್ ಸ್ಟ್ರೆಸ್ ರೆಪ್ರೆಸೆಂಟ್ ಮಾಡುತ್ತೆ. ಇಲ್ಲಿ ಸ್ಟ್ರೆಸ್ ಆಫ್ ದಿ 2 ವೈಯರ್ ಸೇಮ್, ಬಟ್ ಸ್ಟ್ರೇನ್ ಕರಸ್ಪಾಂಡಿಂಗ್ ಟು ವೈಯರ್ ಕ್ಯೂ ಈಸ್ ಮೋರ್ ಕಂಪೇರ್ ಟು ದಟ್ ಆಫ್ ಆರ್ ಕಮ್ಮಿ ಇದೆ. ನಾವು ಲುಕ್ ಅಟ್ ದಿ ಕರ್ವ್ ಥರ್ಡ್ ಒನ್ ವಿಚ್ ಇಸ್ ಹ್ಯಾವಿಂಗ್ ಮ್ಯಾಕ್ಸಿಮಮ್ ಆ್ಯಂಗಲ್ ಜಾಸ್ತಿ ಇದೆ. ಆ್ಯಂಡ್ ಆ ಕರ್ವ್ಗೆ ಸ್ಟ್ರೆಸ್ ಈಸ್ ವೆರಿ ಲೆಸ್, ಸ್ಟ್ರೆಸ್ ರಿಕ್ವೈರ್ಡ್ ವೆರಿ ಲೆಸ್ ಲೈಕ್ ರಬ್ಬರ್. ವೆರಸ್ ಎಸ್ ಕ್ಯೂ ಎಸ್ ಆರ್ ಲೈಕ್ ಸ್ಟೀಲ್, ಜಾಸ್ತಿ ಸ್ಟ್ರೆಸ್ ಬೇಕು. ಅಲ್ಲಿ ಫಾರ್ ಪಿ ದಿ ಸ್ಟ್ರೇನ್ ಈಸ್ ಸೇಮ್. ಇಲ್ಲಿ ಏನು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ತೀರಾ? ಸ್ಟ್ರೇನ್ ಕರಸ್ಪಾಂಡಿಂಗ್ ಟು ದಿ ಕರ್ವ್ ಪಿ ಈಕ್ವಲ್ ಟು ದಟ್ ಆಫ್ ಕ್ಯೂ, ಬಟ್ ಸ್ಟ್ರೆಸ್ ಕರಸ್ಪಾಂಡಿಂಗ್ ಟು ಪಿ ಈಸ್ ಲೆಸ್ ದಟ್ ಆಫ್ ಯಾವುದು? ಕ್ಯೂ. ದಿಸ್ ಇಸ್ ವಾಟ್ ಯು ಅನಲೈಸ್ ಫ್ರಮ್ ದಿಸ್. ನಾವು ಇಫ್ ಯು ಕಮ್ ಟು ದಿ ವೈ ವ್ಯಾಲ್ಯೂ, ಎಲಾಸ್ಟಿಕ್ ಲಿಮಿಟ್, Young's modulus inversely proportional to tan theta, because 1/tan theta ಮಾಡಿದಾಗ y which is stress by strain ಈ ಕರ್ವ್ಗೆ. ಹಾಗಾಗಿ ದಿ ಕ್ವಾಂಟಿಟಿ ವಿಚ್ ಇಸ್ ಹ್ಯಾವಿಂಗ್ ಮೋರ್ ಆ್ಯಂಗಲ್ ಮಸ್ಟ್ ಬಿ ಹ್ಯಾವಿಂಗ್ ಲೆಸ್ ಆರ್ ಮ್ಯಾಕ್ಸಿಮಮ್ ಆ್ಯಂಗಲ್, ಮಿನಿಮಮ್ ಎಲಾಸ್ಟಿಸಿಟಿ. Y minimum, elasticity minimum. Y maximum, elasticity maximum. That's what you need to remember, because Y, Young's modulus, stress by strain. Stress more, Y more, or elasticity more. ಇಲ್ಲಿ ಟ್ಯಾನ್ ತೀಟಾ ಜಾಸ್ತಿ ಇದ್ದರೆ ವೈ ಕಮ್ಮಿ, ಬಿಕಾಸ್ ಇನ್ವರ್ಸ್ ರಿಲೇಷನ್. ಈ ಗ್ರಾಫಿಗೆ ಇನ್ವರ್ಸ್ ರಿಲೇಷನ್, ಬಿಕಾಸ್ ಸ್ಟ್ರೇನ್ ವರ್ಸಸ್ ಸ್ಟ್ರೆಸ್ ಕರ್ವ್ನಲ್ಲಿ. ರಿಮೆಂಬರ್ ದಿಸ್, ಸ್ಟ್ರೇನ್ ವರ್ಸಸ್ ಸ್ಟ್ರೆಸ್ ಕರ್ವ್ನಲ್ಲಿ modulus of elasticity or Young's modulus inversely proportional to tan theta. More is the angle, less is elasticity. ಅದೇ ಸ್ಟ್ರೆಸ್ ವರ್ಸಸ್ ಸ್ಟ್ರೇನ್ ಕರ್ವ್ನಲ್ಲಿ Young's modulus is proportional to tan theta. ಅಲ್ಲಿ ಥೀಟಾ ಜಾಸ್ತಿ ಆದರೆ ವೈ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. ಈ ಡಿಫ್ರೆನ್ಸ್ ಗಮನಿಸಬೇಕು. ನೋಡಿ, ಫಾರ್ ದಿ ಫಸ್ಟ್ ಕರ್ವ್ ದಟ್ ಈಸ್ ಪಿ, ಆ್ಯಂಗಲ್ ಮ್ಯಾಕ್ಸಿಮಮ್ ಅಂದರೆ tan theta maximum implies y is minimum. But look at the options. Option A says elasticity of wire P is, elasticity implies what? Young's modulus. Young's modulus ಅದು ನೆನ್ಪಿಟ್ಕೋಬೇಕು. ಎಲಾಸ್ಟಿಸಿಟಿ ಅಂದರೆ ಯಂಗ್ಸ್ ಮಾಡ್ಯುಲಸ್ ಜಾಸ್ತಿ ಅಲ್ಲ, ಮಾಡ್ಯುಲಸ್ ಆಫ್ ಎಲಾಸ್ಟಿಸಿಟಿ ಜಾಸ್ತಿ ಇದ್ದರೆ ಮೋರ್ ಎಲಾಸ್ಟಿಕ್ ಅದು. ಹಾಗಾಗಿ ಯಂಗ್ಸ್ ಮಾಡ್ಯುಲಸ್ ಆಫ್ ಪಿ ಮ್ಯಾಕ್ಸಿಮಮ್ ಹೇಳ್ತಾರೆ, ಬಟ್ ಇಟ್ ಈಸ್ ರಾಂಗ್. ವೈ? ಆ್ಯಂಗಲ್ ಮೇಡ್ ಬೈ ದಿ ಕರ್ವ್ ಪಿ ಈಸ್ ಮ್ಯಾಕ್ಸಿಮಮ್. Angle maximum, y minimum. In fact, y is minimum, not maximum. So option wrong. Look at the option B. Elasticity of wire Q is maximum. ನೋಡೋಣ, ಈಗ ಎಲಾಸ್ಟಿಸಿಟಿ ಆಫ್ ಕ್ಯೂ ಜಾಸ್ತಿ ಆಗಬೇಕು ಅಂದರೆ ಆ್ಯಂಗಲ್ ಮಸ್ಟ್ ಬಿ ಮಿನಿಮಮ್ ಆಗಬೇಕು. ಬಟ್ ಕ್ಯೂಗೆ ಆ್ಯಂಗಲ್ ಇಂಟರ್ಮೀಡಿಯೇಟ್ ಇದೆ. ಇಂಟರ್ಮೀಡಿಯೇಟ್ ದಟ್ ಆಫ್ ಯಾವುದು? ಪಿ ಆ್ಯಂಡ್ ಆರ್. ಆರ್ಗೆ ಮಿನಿಮಮ್, ಕ್ಯೂಗೆ ಮ್ಯಾಕ್ಸಿಮಮ್. ಹಾಗಾಗಿ ಆ್ಯಂಗಲ್ ಕಮ್ಮಿ ಇದ್ರೂ ಎಲಾಸ್ಟಿಸಿಟಿ ಆಫ್ ಕ್ಯೂ ಈಸ್ ಮೋರ್ ಕಂಪೇರ್ ಟು ಪಿ, ಬಟ್ ಲೆಸ್ ಕಂಪೇರ್ ಟು ಆರ್. ಯಾಕಂದರೆ ಆರ್ಗೆ ಆ್ಯಂಗಲ್ ಮಿನಿಮಮ್. ಥೀಟಾ ಮಿನಿಮಮ್ ಇಲ್ಲಿ ಇಂಪ್ಲೈಸ್ ವೈ ಮ್ಯಾಕ್ಸಿಮಮ್. ದಟ್ಸ್ ವೈ ಅಫ್ಕೋರ್ಸ್ ಕ್ಯೂದು ಎಲಾಸ್ಟಿಸಿಟಿ ಗ್ರೇಟರ್ ದೆನ್ ಪಿ ಬಟ್ ಲೆಸ್ ದೆನ್ ಆರ್. ಯಾಕಂದರೆ ಅದ್ರದ್ದು ಆ್ಯಂಗಲ್ ಮೋರ್ ದೆನ್ ಆ್ಯಂಗಲ್ ಕರಸ್ಪಾಂಡಿಂಗ್ ಟು ಕರ್ವ್ ಆರ್. ಹಾಗಾಗಿ ದಟ್ ಈಸ್ ಆಲ್ಸೋ ರಾಂಗ್. ಲುಕ್ ಅಟ್ ಇನ್ನು ಥರ್ಡ್ ಆಪ್ಷನ್ ಹೇಳಿದ್ದಾರೆ, ದಟ್ ಈಸ್ ಟೆನ್ಸೈಲ್ ಸ್ಟ್ರೆಂತ್ ಆಫ್ ಆರ್ ಈಸ್ ಮ್ಯಾಕ್ಸಿಮಮ್. ವಾಟ್ ಈಸ್ ಟೆನ್ಸೈಲ್ ಸ್ಟ್ರೆಂತ್? ಯು ಹ್ಯಾವ್ ಲರ್ನ್ಟ್ ಇನ್ ಯುವರ್ ಸ್ಟ್ರೆಸ್ ಸ್ಟ್ರೇನ್ ಗ್ರಾಫ್. ನೋಡಿ, ದಿ ಸ್ಟ್ರೆಸ್ ವರ್ಸಸ್ ಸ್ಟ್ರೇನ್ ಗ್ರಾಫ್ ಇನ್ಕ್ರೀಸಸ್ becomes maximum, that is called elastic limit, up to that limit. If you increase stress, the body regains its original configuration, that is elastic limit, beyond which it does not regain original shape, size, configuration. If you increase stress, strain also increases, but somewhat like this. Somewhere here the wire breaks. That portion not explained here for Q1P. Q1P ನಲ್ಲ explain ಮಾಡಿಲ್ಲ. ಹಾಗಾಗಿ data is inadequate to decide whether tensile strength is maximum for R or maximum for Q. That's why you cannot go with that also. So appropriate option ಯಾವುದು? D ಹೋಗ್ತೀರಾ. You will move on. Next one, children, on bulk and rigidity modulus. The spherical ball contains volume 0.01%. How do you write 0.01%? Here itself will clear this. 0.1 by 100. That is. So volume decreases by, that's what he says. It cannot contains, contracts. You write contracts. Volume decreases. So change in volume to initial volume is this. When subjected to a normal uniform pressure, 100 atmosphere, that is 100 atm. You think like this. Here itself you have to clarify all these things while reading itself. What is 100 into 1 atmosphere? 1 atmosphere is 1.01 10 power 5 Pascal. As it is a CET or Neet question, we're going to approximate the answer, multiple choice question. That's why instead of writing 1.01, they just write 1 10 power 5. That's it. In Newton Pascal. Pascal means Newton per meter square. 100 10 power 5. That's it. The bulk modulus of the material is in dyne per centimeter squared. Dyne per centimeter squared you have to write. And I will come to this. What is the value or expression for bulk modulus? Bulk modulus is pressure, change in pressure divided by volume ratio, change in volume by initial volume. That is the bulk or volume strain. What is delta P? 100 atmosphere 10 to the power 5 Pascal, right? Newton per meter square. Divided by volume 0.01 divided by 100. So I write this is 20, 10 power 2, 10 power 2, 10 power 5. Denominator, there is 10 power minus 2, and this 100 comes to numerator, becomes 10 power plus 2. So the final value 5 plus 2 7, and this 10 power minus 2 comes to numerator, so it becomes minus 2 numerator plus 2 plus 2 plus 2 plus 4 plus 4 plus 6 plus 5 plus 11 is the value. If you simplify it further, you will get 10 to the power 11 totally. 11, what is the unit? Newton per meter square. He wants it in dyne per centimeter square. How do you write or how do you convert unit? 1 Newton is 10 to the power 5 dyne. We learnt last year or first year units and measurements. Divided by centimeter. 1 centimeter is 10 power 2 meter. 1 meter is 10 power plus 2 centimeter. That whole squared. Remember this, 1 Newton 10 to the power 5 dyne. Unit conversion, we learned this. And 1 meter is 10 power 2 centimeters. 2 twos are 4. So power is 11 10 to the power 5 divided by denominator 4. Bring it to numerator, minus 4. Minus 4 plus 5 plus 1 plus 1 plus 11 plus 12. That is dyne per centimeter square. So we'll go with the option that is 1 10 power 12, option C. Next one, the compressibility of water 4 10 power minus 5 per atmospheric pressure decrease in the volume of 100 centimeter square of water under pressure 100 atmosphere will be. Nodi, pressure is 100 atmosphere, volume is 100 centimeter cube, and compressibility given. Now, what is compressibility is already been explained. It's nothing new. You can analyze here itself. Compressibility is a reciprocal of bulk modulus. So K 1 by C or B bulk modulus. What is bulk modulus? Bulk modulus is, we can write this way, delta P, change in pressure, divided by delta V divided by V. So you can solve for bulk modulus. Bulk modulus K you want. Bulk modulus is that is B, I'll write B that is equal to P divided by delta V by V. We'll start like this because while cross multiplying some mistakes have occurred here. We'll see that now. You solve this way, PV divided by delta V, right? You transfer delta V to the left side. That's what you have to find here. Delta V is PV divided by B. What's B? 1 by B. But 1 by B, reciprocal of bulk modulus is C, compressibility. That's why delta V that equal to PV into C, where C is compressibility. Put the values. Delta V, P is 100 atmosphere, 100 ATM into V. What's V? 100 centimeter squared into what's C? 4 10 power minus 5 per ATM divided by 1 ATM. So ATM cancels. So here 2020, finally 4 10 to the power minus 1. Here minus 5 plus 2 minus 3 plus 2 minus 1. 4 10 power minus 1 is 0.4. 0.4 centimeter square is the answer. Next, a thick uniform rubber rope of density 1.5 gram per centimeter cube and Young's modulus 5 10 power 6 Newton per meter square has a length 8 meter. When hung from a ceiling of a room, the increase in length of the rope due to its own weight. We discussed the same problem as a formula previously, maybe 5 or 6 problem. Watch it once again. This formula we derived. The rest is simplification, you practice it. But only thing I would like to explain once again, density is 1.5 gram per cc centimeter cube. You have to write that in kg per meter cube because SI unit. That's why all values are in SI remaining except this. That's why 1.5 gram 10 to the power minus 3 kg divided by cc 1 centimeter 10 power minus 2 meter whole cube. 10 power minus 2 3 is a minus 6. So the value is 1.5 10 to the power minus 6 comes to numerator. Minus 6 plus 3 is plus 3. So the value is 1500 kg per meter cube. This way you will use that value for rho. That's finished. He has used that here 1500. Now once again, how this formula comes? What is this actually? See, there is a rope hanging down from a rigid support. The length of the rope is L, right? ಈಗ center of mass of the rope uniform ಆಗಿರೋದ್ರಿಂದ exactly center ಅಂದರೆ this length becomes what? L by 2. So weight acts down, weight W, that is the force exerted over this half length, that is equal to mg. Now you want to find the Young's modulus, that is F divided by A into L by delta L, right? You want to find extension, that is delta L, F divided by A, L by Y, right? He has given area, right? Area, and also length. For length, what do you write here? Mass. What is force? Force is weight, its own weight. That's equal to mg. What is m? M is density into volume into g. What's a volume? S is a cylindrical wire, length into area into g. And L, for L you write L by 2, L by 2, L by 2. And L by 2. Here. This extension, this is L by 2. And this L is full L. E L ಇದೆಯಲ್ಲ ಅದು full L. Small L. ಯಾಕಂದರೆ full length of the wire having mass M. That's why ನೋಡಿ ಇದಕ್ಕೆ ನೀವೇನು ಬರೀತೀರಾ? full L ಬರೀತೀರಾ. ಇದು L by 2 ಬರೀತೀರಾ. So you write delta L that equals to, instead of mgf you write mg. Mg is rho times length L into A into G, that is what? Weight divided by A. See here, A cancels, into L by 2 divided by Y. So you have half ಇದೆ rho GL square divided by Y. That's the value of delta L. What is delta L? Increase in length of the wire. That's it. Now on energy stored in elastic materials, potential energy actually. Problem 29. When an elastic material with Young's modulus Y subjected to a stretching stress S, the elastic energy stored per unit volume. I explained you what is potential energy stored in a wire. In video 1, last part, you watch it again. You go to that video, watch it again, come back. Remember, note down those relations. Now you use it. Half into stress into strain. Half into stress into strain into volume of the material. This potential energy per unit volume is half into stress into strain. Half into stress into strain is the formula. Or if you write Young's modulus, what is stress? Stress is Young's modulus Y, stress by strain. For stress, what do you write? Young's modulus into strain. Strain into strain, strain squared. So you can write this way also. That is potential energy per unit volume. Now we'll come to the solution part. Y, half of Ys, half S by Y, half S square Y, half S square by Y. It's very simple. As I told you, energy per unit volume. This is energy, potential energy per unit volume. Half into stress into strain. For strain, what do you write? That's what? Young's modulus stress divided by strain. Stress by strain. So you solve for stress. If you solve for stress, it becomes strain into Y. If you solve for strain, it becomes stress by Y. You just transfer this way. So stress by Y. So half into stress square by Y, because he wants it to express in stress. Stress S ಅಂತ ತಗೊಂಡಿದ್ದಾರೆ ಅವರು. ಹಾಗಾಗಿ stress square divided by Y. Very simple substitution. Now we'll see next one based on work only. If the work done in stretching a wire 1 mm is 2 joule, the work necessary for stretching another wire of the same material but with double the radius and half the length by 1 mm in joule is. You have to find the amount of work done to stretch it by half. Now first of all, you convert the relation half into stress into strain. This is the formula. This is energy per unit volume. This is actually work done in stretching a wire. Work done half into stress into strain. That's actually half into stress into strain, but into volume actually, into volume. He has brought volume to the denominator. That's why work per unit volume. This is what? You have to add that word in the question. Work per unit volume. That's equal to half into stress into strain. Half into stress into strain. Stress, this force per unit area is a cylindrical word. That's why pi r square. That's it. Into strain, change in length by original length. That's what. Now he says, in both the cases, change in length is 1 mm, 1 mm, 1 mm. So delta L is a constant for a given force. That's why force also constant. Therefore, this work per unit volume, potential energy stored per unit volume In the first case, proportional to radius here, W by V proportional to 1 by R square, 1 by L. 1 by R square into L. R1 square, L1 square. Similarly, work per unit volume in the second case proportional to R2 square, L2. What do you write? Work in the second case, he wants the ratio, right? Per unit volume. Per unit volume, second case divided by work per unit volume, first case, that equal to inverse relation. That's why R2 denominator, L2 denominator. Numerator R1, L1. R1, R2 ratio whole squared. L1 by L2, that's it. Simple. He says the length, radius is 1 for R1 and 2 for R2 whole square into new length is 2 times initial length. Right. That's why you can easily solve and write it is 2 into 1 by 4, right? 2 into 1 by 4. 2 into 1 by 4, that's equal to around 1 by 2. Yes, that's it. Half. And you solve for work per unit volume second case. Half of work per unit volume first case. Work per unit volume first case is 2 joule. So half of 2, 1 joule. That's it. It's very simple. Here, not just W, it is W by V, work per unit volume. That way you think. Next, a wire of length L, cross-sectional area A is made of material Y, Young's modulus Y. The work done in stretching the wire by an amount X is extension X, length L, area A, Young's modulus Y. Right? The options YAX by L, YAX combination. No stress involved here. How do you know stress not involved? Force is not there because stress is forced by area, right? Like that you identify. And solution has been shown here. Short. I will explain this solution. How do you start? Work. What is work? Work is half into stress, right? Into strain, into volume, right? According to Young's modulus definition, what is Y? Stress divided by strain. So how do you solve for stress? Stress is Y into strain. Strain into strain, strain squared into volume. So Y that equal to half of, W equals to half of Y into, what is strain, change in length divided by original length, that is squared, into volume. What is volume of a wire? Length into area. That's it. Length into area. Now, W that equal to half of Y, X square by L square, LA, one term cancels. So, you have half into Y, X square A divided by L. So, I'll go with the option B. Right. Last bit one. A rubber cord catapult has cross-sectional area 25 mm square. And its initial length of the rubber is 10 centimeter. It is stretched to 5 centimeter and then released 5 centimeter extension, right? To project a missile 5 gram. Y of rubber, Young's modulus 5 10 power 8. Velocity of projectile is. As children, is a continuation of previous problem. In previous problem, we discussed work done for an extension X. Initial length L, area of cross section A. Now this work done, how does it appear? According to our work energy theorem, work done is equal to change in kinetic energy. Initial kinetic energy of a stone in the catapult, catapult will be like this, Y-shaped with 2 rubber bands tied like this. This is the stone fixed here, that is missile here. Initially, it was at rest, so initial kinetic energy is 0. When you pull it and release, you will give it with the kinetic energy. What is kinetic energy? Half mv square. If it moves with velocity, v. And that is from work done by the elastic force. Work done by elastic force, that is elastic potential energy, this expression. y x square a divided by L. So remember these as expressions. That's the idea. How much interrelations you remember, that always strengthens you. That's very, very important. You always follow it. So you solve for v. When you solve for v squared that equal to root of, you go, half cancels, m goes that side, denominator y x square a divided by m into L. If I remove root, square here, it becomes root. I'll put this values here and done simplification. You follow this to save time. I have already put the values. Y, this value, this 25 10 power minus 6, 25 10 power minus 4 divided by m 5 gram 5 10 power minus 3 and L 10 centimeter 10 10 power minus 2 meters. So you get a value around 250 meter per second. Check it out once. So it is a connection between work density theorem. Work is work done by elastic force, which is elastic potential energy. For a extension x, energy expression is this, half y x square al. How do you get it? From this basic relation, half into stress into strain into volume. Like that you think. You keep solving problems, students. So these are the main topics, applications, interrelations covered in most of the CET NEET type examinations. If you remember these, you are thorough with the concepts. Only thing is, you watch this video once again thoroughly, remember all the interrelations, keep practicing. Practice ಮಾಡ್ತಾ some more interrelations you will develop. That is preparation. ನೀವು ಯಾವುದೋ ಒಂದು ಸರಿ ನೋಡಿ ಬೋರ್ಡ್ ಎಕ್ಸಾಮಿಗೆ ಪ್ರಿಪೇರ್ ಆಗಿಬಿಟ್ರೆ ಅದು ಮುಗಿಯಲ್ಲ. ಇದು ರೆಗ್ಯುಲರ್ ಪ್ರಾಕ್ಟೀಸ್ ಮಾಡ್ತಾನೆ ಇರಬೇಕು. ಯು ಹ್ಯಾವ್ ಟು ಹ್ಯಾವ್ ಪೇಷನ್ಸ್, ಕಮಿಟ್ಮೆಂಟ್ ಆ್ಯಂಡ್ ಬಿ ರೆಗ್ಯುಲರ್. ಯು ವಿಲ್ ಕಂಟಿನ್ಯೂ.